Assalamu alaikum. Dear students, today we will start with our new subject for this semester, which is control systems. Now, I have to go a little bit quickly because the video, when it becomes too long, there is a difficulty of uploading it. So we will have to summarize. I have to summarize them, and then you have to look into the lecture notes which I email you normally. Okay, let's start with the definition of a system first. Now, what is a system? A system is some sort of combination of different components which is supposed to accomplish a certain function. Now, when we talk about a control system, now this set of components has to work in coordination, and then there is an objective function, and that objective function is supposed to be defined within certain limits. For example, let's talk about a simple amplifier. Now, any amplifier, for example, when it is supposed to be a control system, we have an input and we have an output. Now, let's say this is something to do with the voltage, and this voltage is in terms of the dBs when we turn towards the output quantity. So, what a system actually does in general, that is, it accepts a certain input and then it produces a certain output through processing. Those components which I have already mentioned are supposed to process that particular quantity and convert them into something like dBs. Let's take this as an example. Now, again, we have to make sure that this particular quantity which is output is supposed to be within certain limits. Let's say between some levels L1 and L2. Now, all the time, whatever are the changes in the input, the output must be within the limits L1 and L2. So, in this case, this is supposed to be then termed as a control system. Now, any variation, for example, will tend to maintain this within the desired limit. Now, that limit is rather sometimes very narrow or a little wider. That depends upon the requirement. But nonetheless, the system must be stable at all times. So this is one important feature of any control system. So any system can be defined as something to do with set of components which are working as a team or teamwork, and then they process an input and give you the desired output. But anyhow, when we talk about a control system, something else is there, and that is the proper coordination. And then it is an objective function to maintain quantities between, let's say, L1 and L2. Despite any changes, any drastic changes in the input quantity. As a matter of fact, if you look into the real world, something which is not a controlled system, if there is any increase in the input, there is a decrease or increase in the output. That depends upon what type of a system it is, and eventually that decrease or increase is not actually quantifiable in terms of what you desire. So that doesn't make that as a control system. So in a sense, a control system is supposed to fulfill certain objectives, objective function, which is our desire, what we want from that system. Now, talking about a control system, or let's first of all talk about a system in general. We have, for any system, you must have an input. Now, it must give you an output. That's a property of the system. And then the system is made of some components. Now, those components can be in different configuration or arrangement to accomplish a certain task. However, when you talk about a control system, we need something special. And before we discuss this something special anyhow, let's first of all have some idea about the different type of control system which we have in our engineering systems. The first one is the open loop control system, and the second one is a closed loop control system. Now, in general, when we talk about control system, we define input by certain variable which is RT. As a matter of fact, we use T domain to signify that something is to do with the real-time quantity. Now, the Laplace transform is written as Rs. Now similarly, the output is defined as Ct in time domain, or capital C S when we talk about the Laplace transform of this one, that is in frequency domain. Now similarly, all the components together are actually modeled by certain mathematical expression. Now when we talk about the time domain, this mathematical expression is actually the impulse response. You must have studied that in signals and system. Now when we talk about in frequency domain, this is called a transfer function. We will come back to the transfer function later on, because this is one of the most important element of any control system analysis and design. Now let's first of all talk about a simple open loop system. Now the simplest possible diagram can be looked upon as such. That is, we have a plant. Plant means something to do with the processing. So it accepts a certain input, it processes it, and it gives you the output. Now in this type of system, it's an open loop because there is no communication between the input and the output as such. That is, the input doesn't know what is happening in the output. So this means that it does not have any corrective measures in order to maintain the output between certain limits. So this is basically an open loop system. Now it's silly to call this one as a control system, but nonetheless it is controllable in a sense that it can be, the components can be designed to fix that particular quantity. But nonetheless, we are not talking about here certain sensitivity functions like temperature, pressure, etc. But then we come to the closed loop control system. Now closed loop control system in real life is looking like an actually control system. Now the difference is that we add two components in addition to the one which you have in open loop system. The first one is the feedback element. Now this is a very important component of a closed loop system. The plant is still the same. Then we have something like a summation point or a comparator, whereby in this case signals are compared. Now what happens in this case, we do have something like two additional variables. One is ES. ES is supposed to be the error signal, and BS is supposed to be the feedback quantity. Now what is actually happening in this case is that the input actually has certain communication with the output through feedback. Now whenever we talk about feedback, we have placed a system of communication between output and input quantity. For example, once you obtain your degree, and then when you go out from this university, and if there is no feedback, there is no communication between the university authorities and you, then what will happen? We will not be able to correct things in a sense that we have to make sure that we get feedback from the alumni, and through that feedback we will have some sort of a desired corrective measures in order to maintain some standards. Now in this case, what happens, the input has a communication through the feedback element. That communication is compared, and then an error signal or corrective measure is generated to drive the plant accordingly in order to maintain this quantity what actually we want. So in fact, what we can define over here, input and output more, you can say in a very precise manner. The input is the desired response of the system. Output is the actual response. Now, if the desired and actual response matches, that is, they are within the bounds of what we want, then the system is supposed to be stable. And in fact, all the control systems are designed for stability. Remember, the most important feature of a control system, any control system, is the stability that we are looking for. So in this case, what happens? Any changes in the output quantity beyond the limits will be reported through the feedback device, and it will be compared with the reference input. Now this will act as a reference input. Now this means that the desired value is compared with what actually we get from the output. Now, the plus minus or whatever the case is reported as an error to correct the plant processing so that we get the output what actually we want. So in fact we can say adding a loop over here through the feedback element makes this system as a closed loop system. Now more precisely we can say that the plant must have something like a controller. Now the plant can be combined with the controller in one box or in one block, or it can be separated as such. So a controller is necessary, which is again a very important element. It is with the plant, and that controller actually generates what is called the actuating signal. Actuating signal is the one which is driving the plant. So it actually senses the error, it measures the error, and do the things accordingly what it is programmed for. And then accordingly it generates an actuating signal to drive the processing plant to maintain the output within the limits. Now, as such, most of the desired control system are the closed loop control system. Now, when we talk about the control system, whether it's an open loop or it's a closed loop, it has to perform certain function. Now this means there is some sort of a correlationship between input and output, or you can say cause and effect relationship between input quantity and output quantity, and that is defined by the system function or the plant function, whatever the case is, it is called a transfer function. Now the transfer function is always in the Laplace transformed mode, that is the time domain quantity is converted to S domain. Now remember, I did circuit analysis with you in your third semester. Now in that case we did some differential equations, if you remember. Now to start with, I'll say that we will always be talking about a causal LTI system. Now our systems which are generally considered in this entire course will be causal LTI system with a single input and single output. So let's make it more simple in this case. That is, if we have, for example, a differential equation, let me just write a differential equation in general form. Let's say it is a d square y t by dt square plus b dy t by dt plus c y t is equal to, let's say, x, I'll just write it like this, dxt by dt plus 2xt. I'll write it more, let's say, quantitatively anyhow. So in this case, what we are looking at a differential equation which is defining some system. Now that system may be anything, but nonetheless we are looking for a general differential equation. Now in order to get the transfer function or model a system in terms of transfer function, we have to take the Laplace transform of both sides. Now we will not consider the initial conditions in this case. We will consider all the initial conditions set to 0. So if we take the Laplace transform of the first term, this is xs. Now the second term is bs, sorry, I'm just using y. So it will be ys. And then we have c ys is equal to s xx plus 2xs. Now this is what we have the S domain of this T domain expression. Now when we talk about transfer function, we have to, in particular, we have to have something like output quantity divided by input quantity as a ratio. We will be looking at a ratio. Now in this differential equation, it is understood that this yt is the output quantity. So yt is the output quantity. So in this case, ys is supposed to be the output quantity, and xs is the input quantity. So we have xs. Now the transfer function is obtained in this manner. Now in this case, if we have something as this differential equation transformed into S domain, we will be getting something like S plus 2 divided by a s square plus bs plus c. However, one thing we must remember that we should not actually have any constant multiple with the highest power of s neither in the numerator nor in the denominator. So in the numerator we have nothing with the highest power of s. However, in the denominator we have a. So we have to take this thing common. Now taking common, a is taken as common. So we have something like ba divided by ca. Now we can write this one as 1 over a into s plus 2 divided by s square plus, let's call it capital AB, and then we have capital, this one is s, and then we have capital B. Let's say now we are looking at this particular expression. Now this particular expression is in general form looking as such. We have three quantities. One is this quantity, which is K. One is this quantity, which is PS. And one is this quantity, which is QS. Now these three are important. First of all, K. Now K is called the gain, system gain. Now this is a non-zero quantity and we have particular cases for K. The first case is when we have K between 0 and 1. So this makes the system as an attenuator. Now we have K greater than 1, it makes the system as an amplifier. Now if we have K less than 0, that is negative. This means it's an inverter. And as a special case, we may have something like K equal to 1, which means our system is a buffer. That is a one-to-one system in fact. So in this case, whatever the value of 1 over a becomes, anyhow, you can compare this with the cases and you can characterize the system accordingly. Now, this particular quantity, which is s plus 2, this is PS. Now, PS is the polynomial expression of the numerator. So, whenever we have PS equal to 0, we will get an equation. So, nonetheless, if we talk about making this as 0, we will get an equation. And solving this equation will give us a root which is minus 2 for the numerator expression. Now, this minus 2 is called the zero of a system. This is called the zero of a system. Why? Because if we put s is equal to minus 2 in this transfer function, by substituting this for any s for s, it will make this entire transfer function equal to 0. Now, then we have Qs. Now, this Qs is very important. This is called characteristic polynomial. Now, the characteristic polynomial, in fact, is the most important quantity of a transfer function beside gain and zeros anyhow. So, Qs, when it is made equal to 0, it forms what is called a characteristic equation. Now, solving this equation will give you roots, which are called the poles of the system. So, if you solve this quadratic equation, this is equated to 0, and you solve it for s, you will get two roots, and these are then called the poles of the system. So we have zeros and poles. But remember one thing, the number of poles and the number of zeros must be balanced. However, we are looking at something like a missing zero, because there are two poles and the zero is missing, one zero is missing. Now where is that zero? We suppose that this zero is lying at infinity. So we summarize things that the gain of the system is 1 over a. The physical zeros is only 1, which is minus 2, and there is 1 0 to balance the poles. It is lying at infinity. However, there are two physical poles. Now remember, poles and zeros may be real, or they may be imaginary, or they may be complex quantities. Now, when they are complex quantities, they always occur in conjugate pairs, remember. This is very, very important function of the poles and zeros. Now, beside poles and zeros physical, you can say, evaluation, we can actually plot them on an S-plane. Now plotting them on an S-plane gives us a very important indication about the stability of the system. You will study this later on, however, but S-plane is actually a complex plane with sigma as a real axis and j omega as imaginary axis. Now any poles and zeros are supposed to be plotted on this S-plane because all these are complex quantities. The transfer function is complex because it is in S domain. S is a complex quantity, remember. So let's plot this 0. Now a 0 is plotted as a circle around that point where it is located. And any pole will be plotted as a cross. Now if they are complex, they must be in the complex conjugate. So let's say that there are two, in fact, poles, and these poles are, from this equation, they are complex conjugate pairs. So we can plot it like this, anyhow it depends. Now we can divide this S-plane into two halves. This one is the right half and this one is the left half. Now if the closed loop poles, remember the closed loop pole, there are open loop poles as well. But if the closed loop poles lie, all the closed loop poles lie in the left half of the S-plane, this means the system is stable. However, there is a special case as well, when all the poles and zeros, that is the closed loop poles and closed loop zeros, are lying in the left half plane, the system is then again stable, but then it is called a minimum phase system. So we have a minimum phase system. We will come to these later on in the course. However, it's just a reminder. So we can, from the transfer function, we can evaluate the zeros, the poles, and then the gain of the system, and then we can find out whether the system is stable or unstable. Now, on top of that, let's remind ourselves about the order of the system. That what is the order of the system? First order, second order, third order. Now, the order of the system is always defined in terms of the degree of polynomial Qs. Now, in this very example, our polynomial was a second order polynomial or a second degree polynomial. So the system is a second order system. Now remember, the order of the system is always defined in terms of the degree of this Qs, which is the characteristic polynomial. That is why it is called the characteristic polynomial. So, and from the characteristic polynomial, we will get the closed loop zeros, and closed loop poles in fact. So these closed loop poles, when are placed in the S-plane, they will remind us whether the system is stable or unstable. Now, transfer function is in fact a very important ingredient of all control system analysis and design. So, in fact, we have to make sure that we understand the transfer function use and how to obtain the transfer function of some systems, whether they are electrical, mechanical or electromechanical system. We have three types of system we will be dealing with. One is the electrical system, then we have the mechanical system, and then we have the electromechanical system. It's a combination of the two. In general, our discussion in this course will be oriented around these three types of system, but most important are the electrical system because they are more versatile. So, in any case, let's first of all deal with electrical system. Now, to get a transfer function of any electrical system, it's very easy. All you have to apply are the simple circuit analysis laws, Ohm's law, KVL, KCL. Now, let's say we have an electrical system. Electrical system is simply a circuit. We are looking at something like a circuit which is like this. For simplicity, let's say the values are all 1 farad, this is 1 ohm, this is 1 Henry. This is I, let's say it's immaterial about whether what is the value of I. We are not interested in transfer function. We are not interested in what is the value of the forcing function. Remember, all the sources are supposed to be the forcing function. So, first of all, the first step in getting the transfer function is to transform this circuit into S domain. That is, take the Laplace transform of each. Now, for the resistance, it's the same 1, 1. However, for the capacitance, it will be 1 over S because it is 1 over SC. The Laplace transform of the capacitor is 1 over SC. For the inductor, it is SL. Now, in this case, it will be simply L. Now, we have completed the task. The first step is over. The second step is decide which tool you want to use for the analysis, and either it will be KVL or KCL. But as a matter of fact, the circuit looks more or less like it's a KCL facilitated circuit. In any case, let's define the output, because I is the forcing function, it is always the input. But what about the output? Let's say the output is the voltage across the capacitor. Let's say this is the volt. Now, transfer function is a ratio not necessary of two similar quantities. It may be dissimilar quantities, doesn't make any difference. The output may be something like a mechanical quantity, input may be an electrical quantity. We are talking about something like transducers. Transducer is some sort of a system or subsystem which is transforming one form of quantity or energy into another form. So most of the times we will be dealing with transducers. So in any case, let's remind ourselves in this case that not necessary that the output and input are supposed to be the similar quantities. They may be, in this case we are talking about the voltage across the capacitor. So all we need is a transfer function of this form. Now this is Is when we transform this into S domain, and this one will be Vs. Now once we decide about which law we are using, I think I'll be more comfortable with KCL. However, it's up to you. So let's say V1 and V2 are the nodal voltages. This is the ground node. I'm not using S anyhow because all the time I won't be using S. I'm just using the capital letters for S domain. So in this case, let's talk about the node V1. So node V1. So current moving towards, and all the currents then must be moving outward. So we have Is is moving towards, and it is equal to the sum of the currents moving outward. So it is basically V1 divided by 1. So it is simply V1, and then we have V1 minus V2 divided by 1, which is V1 minus V2. This gives us this circuit as 2V1 minus V2. So this is our equation 1. You know how to form equations of nodes. Now the second node is this, where the forcing function, there is no active source, so we just zeros. It means that all the currents are supposed to be outward from the node. Now the first branch is V2 minus V1 divided by 1, of course, and then we have V2 divided by 1 over S. So if we have V2 divided by 1 over S, it becomes SV2. And then we have V2 divided by the combination, which is this one is now S1 or simply S. So it is S plus 1. Now if we simplify this equation, anyhow I just give you the home task to simplify these two equations. Now all we actually want over here is something like ratio of V0 by Vs. But what is V0 actually? V0 is the voltage across the capacitor. And in fact, this nodal voltage V2 is same as V0. So we have V0, then we have V0, and then we have V0. So combining all the terms, so we will get V1 on this side, and then we will combine all the V0 terms on the other side. So it will give us something like this. You can simplify this one, and once you've done that, then instead of V1 in equation 2, just put that value, because you need this one. You have to eliminate V1. Our quantity we desire is V2, which in this case is V0. So if this whole expression is substituted for V1 in equation 1, and then you manipulate this one, get the ratio in this form, the function, something which is on the right hand side, is basically the transfer function. So this is an example of a simple electrical system. In the notes you will find an example of another electrical system as such. So let's now come to operation amplifiers. These are the very important ingredient of any control system, because most of the subsystem of control, entire control system, are composed of op-amps, comparator, compensators, controllers, sensors, etc. Most of them incorporate active devices such as op-amp. So op-amp, basically you all know from the field of electronics, but anyhow there are two important modes in which op-amp is used. One is the inverting mode, and then the other is a non-inverting mode. So these are the simple circuit. Now the transfer function of, when we talk about the inverting amplifier or inverting mode of amp, the transfer function is equal to minus Z2, of course in S domain, divided by Z1. But anyhow, for transfer function, do drop this negative sign. This negative sign is simply indication of the inversion. So we don't need it when we talk about transfer function. And for the non-inverting mode, the transfer function will be Z1S plus Z2S divided by Z1S. So in fact, you need not to derive these one. There is no need actually. This is a subject of electronics, but it's simply the use of the expressions over here to get the transfer function. Now, in fact, what we can do actually, in the first case, let's say we have a parallel combination of this one, and then in this one, in this case, we have, let's say, this series combination. And let's say all these are 1, this is 1 ohm, this is 1, just for simplicity. Now, this is V naught divided by V. It is an S domain because I am using capital letters. And in this case also, V naught by V, the transfer function. So this is simple. Now, by definition, what is Z2? It's a series combination of R and C, but that must be in the S domain. So in this case, we will be having a series combination of the two, which is 1,1S. And then Z1 is simply a parallel combination of the two. A parallel combination of the two means this one becomes S and this one is R. So we have S divided by S plus 1. So put those in this equation, simplify, and you will get a transfer function. Simple as that. Now similarly, if we are having something like this as series combination like this is Z1, this is 1, this is S. I am just putting this directly in S domain, and this is then a parallel